Kia ora koutou katoa, it's Mrs. Goodson here, and this is a video about rates of reaction. It's the third video, and it's about measuring rate of reaction. So, in a chemical reaction, we start with the reactants, which are ingredients, and we make products. So, if we want to measure how fast this reaction is proceeding, there are two possible ways. Firstly, we could measure how quickly the products are made, if we can measure the products in some way. And secondly, we could measure how quickly the reactants disappear, if it's easier to measure the reactants. So it depends on the reaction that is happening. So, for example, in this experiment to measure the volume of gas produced, the reactants are in the flask. We've put a bung in the flask and we're collecting the gas. So we would see bubbles of gas, and the gas goes up this collection tube into a syringe, and as the gas is collected, pushes the syringe further down, and so we can measure how much gas has been made. So we put that on a graph. So this along here is time as the reaction proceeds, and then we've got the volume of gas. So as the reaction proceeds, it's going to make more and more gas. The volume of gas in the syringe is going to increase. So we start at the start, there's 0 products because the gas is a product, and then it increases, and there's lots of reactants. The concentration of the reactants is high, and then as the reactants start to run out, the reaction is going to slow down, and then when the reactants run out, we actually need one of them to run out, and then it will stop. So this is measuring the products. A different experiment we could do, the same reaction, is if we had in this flask, we had the reactants, this acid, and in this case, the marble chips. And the gas can leave the flask. So this is important. The gas can go out of the flask and bubbles out. All right, so the cotton wool plug can't stop the gas. It can only stop little bits of spray. So this balance is measuring the mass of what's in the flask and the flask. And so what is leaving will reduce the mass. And so we start out with lots of reactants, and then as the gas leaves, the mass is going to decrease in that. So this graph, the beginning we've got lots of reactant, and then over time the mass of the reactant decreases. So this is measuring the reactants being used up. So we can plot this on the same graph, and you'll see the concentration of the reactant particles will. So this, first of all, this is the products being made, and then this is this one here is the reactants. It's not particularly good drawing. So you get this graph of rate of reaction. This in this picture, it shows the purple particles are the reactant particles, and so we start out with lots of those and no products. And then as the products are made, the concentration, so as we go along this way, the concentration of the reactant particles decreases and the concentration of the products increases until there's no reactants left. They've all collided and reacted. So the purple line shows, as we go down the graph here, shows the reactants being used up, and the green one is the products being made. All right. They both end up horizontal, which means no further change because there's no reaction happening by the time that we get to the end here. So in this graph, the steepest part is the fastest part. Then it slows down, and then when it's flat, there's no change. Okay, so the steepest part is the fastest part. So that is at the beginning of the reaction when the concentration of the reactants is the highest. The reaction happening at the fastest rate is A, okay? And then it slows down for B because the reactants are being used up, and C is when it has stopped. So if we make a change to the reaction, now the things we could change are temperature, concentration of the reactants, surface area of any solids involved, or a catalyst. It's going to speed up the reaction. So at the start is the same, okay? So this one is showing products being used up. So the start is the same. At the start, there's 0 products. But A shows a steeper rise. So we've made a change that sped up this rate of reaction. But you'll notice that both lines end up at the same point where I've drawn an X because the amount of reactant is the same. So this video has described how to set up an experiment to measure the rate of reaction, explained the key parts of a graph of volume or concentration of product versus time for a reaction, and then we've also looked at a graph that compares the rate of reaction when a factor affecting rate is changed, for example, surface area, concentration, temperature, or catalyst, and we see how to draw changes in that graph.